Welcome back to Segment 3 of the CarbonSolutions course on sustainable building materials. In the last segment, we covered a number of standards and certifications that can be used to identify environmentally preferable products. In this segment, we'll look at life cycle analysis versus life cycle costing, explore the various ways that building materials can be sustainable by being regional, rapidly renewable, recycled, reclaimed, contribute to healthy indoor air quality, and provide opportunities for daylighting. Life cycle analysis versus life cycle costing. To understand the environmental impact a building material has during its lifetime, we must follow it from birth to death, or hopefully reincarnation. A life cycle assessment, or LCA, analyzes this impact along each successive step, which includes extraction, which is the sourcing of raw material, manufacturing, how far the product is shipped to market, how the material must be installed and maintained, and recyclability of the material, and if it cannot be recycled, how it must be disposed of. The ultimate goal when looking at the LCA is to compare the complete range of environmental and sometimes even social impacts attributable to products and services, and to choose the ones with the favorable footprint. For example, vegetative roof systems have many environmental benefits over a traditional asphalt roof when their life cycle assessments are compared. An asphalt roof is traditionally derived from petroleum byproducts, does not contain any recycled material, is not itself recyclable, and is disposed of in landfills at the end of its life, which is typically 15 years. If we compare this life cycle to a well-designed vegetative green roof system, we can see that a green roof is smaller in its environmental impact, will require little maintenance, and has a much longer life than a traditional roof. So not only does the vegetative roof have a preferable LCA, it also has a preferable LCC, or life cycle costing. Whenever looking at a product's LCA, it is also valuable to look at and understand its LCC. Life cycle costing is more familiar to the construction industry and its bottom line approach, and takes an economical eye to valuing a product or a system over its lifetime, including operational and maintenance costs and savings. Many times a product's LCA and LCC will be at odds, and it is the job of the team charged with comparing these differences to ultimately decide if the material, system, or service in question is more valuable in terms of greening the project or in greening the bottom line. If when looking at a product's LCA, it is determined that the materials which constitute the product cannot be repurposed and must be landfilled, then the LCA is considered cradle to grave in its life cycle analysis. If, in fact, the product can be recycled into something useful at the end of its life, then it is considered to have a closed loop LCA. A closed loop LCA is also known as a waste to food or cradle to cradle life cycle, a term coined by green architect William McDonough in 2002. In fact, it is possible to certify a product as C2C, cradle to cradle, through McDonough-Bronkhart Design Chemistry, a global sustainability consulting and product certification firm. Founded by McDonough in 1995, MBDC's basic C2C certification requires that all materials and chemicals are assessed for toxicity to human and environmental health, contain no PVC, chloroprene, or related chemical at any concentration, that a strategy is developed to optimize all remaining problematic chemicals, and that all materials defined as technical nutrients are recycled and biological nutrients are composted. C2C products that are designed well can be manufactured and sold for less than standard designs, Cradle-to-cradle materials can perpetually be cycled within closed loops because both the product and its byproducts have value as reused materials. Ultimately, the cradle-to-cradle design seeks to eliminate the need for waste disposal in already overcrowded landfills. Rapidly renewable materials. Rapidly renewable materials are generally considered materials made from plants that are grown to a harvestable maturity in 10 years or less. When utilizing rapidly renewable materials, the primary benefit to the environment is the optimization of land use because dedicated growing space can be rotated sooner. Another benefit to rapidly renewable materials is the CO2 absorption that takes place while the plant is growing. After harvesting, the carbon remains sequestered in the material in a stable state while performing its function in the building structure. In this way, rapidly renewable materials provide a clever method to sink, transport, and safely store carbon, often for long periods of time. An additional gain is realized when harvested products rejuvenate faster than non-rapidly renewable resources. A benefit to using cork, for instance, is that only the cork bark of the tree is harvested, and the tree itself is left to continue to grow in the cork oak forest. These valuable forests support a unique biodiversity of flora and fauna and provide employment to specialized labor valued at over €1 billion annually in Europe alone. A widely known example of a rapidly renewable material is bamboo. One of the fastest growing plants on Earth, bamboo is famous for its ability to reach full maturity in 5 to 6 years and to achieve outstanding hardness ratings. Bamboo is widely used in Southeast Asia as scaffolding, lumber, planks, furniture, and in Western nations often purposed as panels, veneer, solid and laminate flooring, and plyboards. Other globally abundant, rapidly renewable materials include wheat hulls, rice hulls, sunflower seed hulls, soybeans, sorghum, linseed, hemp, coconut palms, and coconut shells. Regional materials. Regional materials are an important consideration when looking at the sustainability of a product. Regionally produced products can reduce both the LCA and LCC costs by minimizing transportation, potentially eliminating overseas shipping and/or long-distance trucking. Regionally harvested, processed, and manufactured products not only reduce the transportation of energy needs, but also direct purchasing power across several stages of the production process to nearby communities, thereby enhancing the local economy. According to BALI, the Business Alliance of Local Living Economies, businesses that make up a local living economy tend to be more sustainable because they are more accountable to stakeholders and the environment in which they are a part. Allowing a purchasing preference to businesses that make a point of, quote, buying local can help a regional economy stay strong and the environmental footprint small. The LEED rating system awards specific points for materials that are extracted, harvested, or recovered and manufactured within a 500-mile radius to the construction site. If, for example, 100-year-old heart pine was recovered from a river in central Florida and shipped to Atlanta, Georgia, and used as flooring, this component would be eligible for regional materials LEED points. On the other hand, if the heart pine was shipped to Austin, Texas, and used there, it would not be eligible as it was recovered beyond a 500-mile radius of the project site. Recycled materials. While as an industry, the building community should try to reduce the demand for materials before we begin looking for ways to recycle them, it is also obvious that there are plenty of materials around that can be repurposed immediately. In fact, The U.S. EPA estimates that over 500 million tons of recyclable material that can be used in construction is produced each year by consumers and industries in the U.S. These materials come in the form of steel, aluminum, glass, agricultural waste, used tires, residues from coal combustion, construction and demolition debris, and sand, among many others. By repurposing general waste and industrial leftovers, landfills are relieved of volume, transportation costs and emissions are reduced, and raw material that would otherwise have to be mined, extracted, or harvested can be conserved for future generations. Given the abundance of used materials that are readily available, it makes sense for the sustainable building community to incorporate recycling and repurposing of materials during construction. The fact that this is achievable and becoming more common is reflected by emerging trends in the sustainable building field. Standards for the International Living Building Institute, ILBI, for example, call for at least 95% of all paper, cardboard, and metals to be recycled during construction of a commercial or residential building. Recycled material is identified by the widely recognized ISO 14021 environmental standard. ISO 14021 defines recycled content as, quote, the proportion by mass of recycled material in a product or packaging, end quote, and requires recycled content be clearly identified as part of an environmental product declaration, or EPD. The three main types of recycled materials are post-industrial or pre-consumer, post-consumer, and post-consumer fiber. Post-industrial, also known as pre-consumer recycled content, commonly indicates that the material or product has industrial scraps and leftovers that have been diverted from the waste stream and have been reincorporated into the manufacturing process. This type of closed-loop recycling often takes place at the facility where it is generated, and sometimes is not regarded as recycling in the true sense. Examples of this include the reuse of sawdust, wood chips, rubber and aluminum scraps, newspaper overruns, fly ash, sunflower seeds, and wheat hulls. Post-consumer waste is generally considered preferable over post-industrial waste. Defined as material that would otherwise be landfilled, post-consumer waste can be repurposed in many new ways. Examples of waste that might be found in a product made with post-consumer recycled content would be plastic and glass bottles, aluminum cans, leftover paint, and metals recovered from used electronic equipment. Post-consumer fiber, or PCF, on the other hand, is usually identified as material discarded after consumer use that has trees and other fibrous plants as their original feedstock. This fiber is commonly recovered from old magazines, telephone directories, office paper waste, newspapers, as well as used cardboard. Examples of products made from PCF would be compostable cups made with recycled paper, or countertops constructed with hundreds of discarded cardboard boxes. Reclaimed materials. Materials that can be salvaged or reclaimed also lower demand on landfills and waste stream infrastructure. Examples of reclaimed material could be bricks once used as subpavement in a road project that are subsequently incorporated in an exterior wall, or 300-year-old wooden posts and beams that are remilled and applied as a living room floor. Salvaged material is often less expensive than virgin or recycled material. What is more, much of this material is distinctive in its quality, workmanship, and aesthetics, often lending unique value to a project. Indoor environmental quality. In this section, we are going to focus on the two main material components that contribute to better environmental quality indoors. They are materials that can improve indoor air quality and daylighting opportunities. Indoor environmental quality has much to do with design, maintenance, and the operations of a building, as it has to do with the type of materials that are used within it. The notion of indoor air quality first gained national attention during the 1970s, when in response to the oil crisis, the U.S. began to implement rigorous energy efficiency measures within new buildings. While buildings became tighter and outside air infiltration was minimized, the heating and cooling systems that recirculated the indoor air started to accumulate indoor pollutants and began to make people inside many buildings sick. Later termed sick building syndrome, SBS is a building occupant health effect that is linked to time spent within a structure where pollutants such as mold, ozone from office equipment, and volatile organic compounds, or VOCs, contribute to poor indoor air quality. Indoor pollutants can come from materials within the building, natural sources, products and equipment brought into the building, as well as occupant behavior such as smoking. When talking about indoor air quality, it is important to distinguish sick building syndrome, SBS, from building-related illness, or BRI. Sick building syndrome describes the phenomena of an acute health or comfort effect experienced by a building occupant. Building-related illness, BRI, is used once an illness is attributed directly to building contaminants. So keep in mind that the two are related but used at different stages. As the understanding of indoor air quality has improved over time, our ability to manage it has also improved. This is important when one considers that as Americans we spend on average 80 to 90% of our time each day indoors. Choosing the right combination of materials, ventilation options, and climate-compatible building design all help avoid indoor air becoming what could otherwise be a collective toxic soup. Now, as we become more aware of the importance of energy efficiency within a building, we are increasingly designing and constructing tightly sealed homes and commercial buildings. If these designs do not consider proper ventilation of fresh air into the building, then engineered flooring, cabinets, and carpets with formaldehyde, paints, adhesives, cleaning products, VOCs from solvents, and even radon-emitting granite can build up to unhealthy concentrations. One easy way to lower the risk of poor indoor air quality is to avoid the use of materials high in toxins, pollutants, and volatile organic compounds, or VOCs. We'll first spend some time looking at VOCs, as they are common across many product types, and discuss how globally policies are going into effect to address their presence in building materials. VOCs are everywhere in our environment. They occur naturally, are typically produced by plants, and are in and of themselves not necessarily harmful. Man-made sources of VOCs include pesticides, solvents, paints, coatings, adhesives, wall coverings, ceiling tiles, furniture, and even office gear such as photocopiers, correction fluid, glue, permanent markers, and cleaning supplies. As these items evaporate, which is natural with a volatile compound, they mix with the air and when inhaled by humans, mix into the bloodstream. Key signs of exposure to VOCs include nose and throat discomfort, headache, allergic skin reactions, nausea, fatigue, and dizziness. At high levels, VOCs can damage the liver, kidney, and central nervous systems. Typically, VOCs are not acutely toxic, but have chronic effects that build up slowly over time. Because concentrations are usually low and symptoms don't show until later on, figuring out what products have VOCs and how much should be a priority during the materials selection phase. It doesn't help much that there is confusion over what levels of VOCs are safe. Added to this is the fact that there are numerous types of VOCs, each with unique properties. The EPA regulates VOCs when they contribute to smog in the atmosphere. This is because some VOCs can react with nitrogen oxides under sunlight and create ground-level ozone and fine particulates, which in turn results in smog. Because of this, the EPA has set standards for VOC limits for only those industrial VOCs that contribute to smog. No standards have been set by the EPA for VOCs in non-industrial settings like office buildings or homes. OSHA, or the Occupational Safety and Health Administration, does regulate formaldehyde, a specific type of VOC, and has adopted a permissible exposure level, PEL, of 0.7 parts per million, which provides some guidance. The point here is that no government agency is actively measuring the off-gassing of chemicals present in building materials. For this reason, it is very much up to the building community to proactively pursue ways in which to minimize and ultimately eliminate potentially harmful chemicals in projects. Identifying toxic chemicals. When considering whether a product has toxic chemicals, we can refer to the product's MSDS, or Material Safety Data Sheet, which can tell us a snapshot of what it contains. However, we cannot tell everything we need to know by this guide, since the EPA does not require the reporting of a toxic chemical that is less than 1% of its complete makeup. That is why it is also important to look to see that the product has Green Guard or SCS, Scientific Certification Systems, seals of approval. These entities provide independent, verifiable, third-party certification of environmental and indoor quality standards and achievements that go far beyond the scope of EPA, OSHA, or information available on an MSDS. One can also refer to California's Proposition 65, which maintains a database of all ingredients that are proven or suspected to be hazardous to human health. We can also look to see whether a product has been tested to meet European formaldehyde emission standards, commonly referred to as E1. To obtain an E1 rating, detectable formaldehyde emissions must be less than 0.75 parts per million, or ppm. Pressure for even more stringent standards in Europe have led to a new ratings classification, E0, based on emissions measuring 0.07 ppm and below. Another avenue for comparison is the Japanese Industrial Standards, JIS, and Japanese Agricultural Standards, JAS, which also test for formaldehyde and assigns 4 levels of emission rates, an F with up to 4 corresponding stars, the highest of which is even more stringent than E0. In contrast, the U.S. does not have comprehensive national requirements that address formaldehyde emissions from floors, cabinets, walls, furniture, and other building components, but California does, and as such, the California Air Resources Board, or CARB, has set the de facto U.S. standards for these emissions. CARB studies suggest that considerable emissions are generated by composite wood products, usually from formaldehydes in the adhesives, and has introduced a 2-phase plan to manage emission levels from particle board, medium density fiberboard or MDF, and plywoods. Phase 1 of the CARB plan, already in effect, requires that formaldehyde emissions measure equal to or less than 0.08 parts per million, a figure that already exceeds OSHA standards. Phase 2, which went into effect January 1, 2010, requires them to be even lower at 0.05 ppm, a standard higher than that of Europe's E0. Beyond formaldehyde, materials can also be engineered and treated with bio-accumulative chemicals. Some water repellents, stain guards, brominated flame retardants or BFRs, chlorinated plastics such as PVC, vinyl, and polyurethanes have been shown to cause birth defects, disrupt reproductive hormones, and compromise immune systems. So, spend some time exploring the various certification processes, the chemical checklists, and online databases, and familiarize yourself with the chemicals that can be commonly found in building products. You'll find that, though somewhat daunting at first, you'll be able to categorize them into groups and learn to assess the concentration levels and distinguish between not so safe and much safer product lines. To reiterate, indoor air quality is still a relatively new area of concern and study, and there is little oversight from government agencies in the fast-evolving universe of building products. Though globally, some governments have started to regulate particular types of harmful chemicals, it is really up to the building industry to use the material selection process as a way to minimize the potential for building occupant risk. Daylighting. Architectural daylighting is at the heart of sustainable building design. When added skillfully, buildings that have efficiently distributed daylight can increase the comfort of occupants and reduce the electrical lighting load, especially in expansive spaces. Schools, warehouses, and offices that operate primarily in the daytime can quickly reap the benefits in energy savings and human productivity associated with improved daylighting. Many studies have shown the positive effects that daylighting has on the human body. Scientists have found that the changing intensity and duration of sunlight can affect our internal biochemistry. Exposure to daylight is known to increase the production of vitamin D, for example. This should come as no surprise, since humans have lived in concert with the sky for thousands of years. Beyond our natural affinity for daylight, studies have proven that daylighting affects a person's mood. One example of this is found in seasonal affective disorder, a seasonal pattern of unipolar and bipolar mood disorders. Studies have also shown that sufficient and efficient daylighting can improve worker productivity. For instance, studies on the cost of owning and operating buildings over time, which quantified the effect of daylighting on human performance, found a drop in absenteeism, improved levels of concentration, employees processed calls faster, and there was an improved sense of well-being. Although lowered electricity use is a potential benefit of having skylights, solar light tubes, and larger window areas, effective daylighting designs must block heat to optimize life cycle costs. The better daylighting products are at reflecting radiation, the lower the building's cooling load will be. What is more, if systems such as occupancy and lighting sensors are used in conjunction with daylighting, savings in cooling and electricity loads are even more likely to be realized. Light tubes are particularly well suited for harvesting and focusing daylight into interior spaces. Using Fresnel lens technology, these devices capture direct and indirect light, making the most of the day's cycle, augmenting even the scant light present in early morning and late afternoons. Once captured, highly reflective tubing carries daylight over long distances, across several stories, and can even curve around bends. From the interior, these daylights appear as conventionally designed recessed lights, integrating well into ceiling design. The adaptable nature of tubular daylighting solutions allow architects and design teams to choose the optimal location of the lens on the roof, while providing flexibility for where the natural light is ultimately delivered. Other key advantages of tubular lighting are the low thermal heat transfer properties and minimal operational and maintenance costs. As we have seen, there is a range of sustainable attributes and standards that we should look at to help us settle on the best choice of materials for a project. As with all decision-making processes, there will be trade-offs of some attributes for others. Project teams may decide that less formaldehyde in their engineered flooring is more important than 50% recycled content carpet. Building owners may settle on less expensive materials from overseas over a competitively priced regional alternative that may support the local economy. A project specifier may recommend a material that is easily recyclable but requires more maintenance over a product with disposal issues because in the final analysis, the LCA outperforms the LCC. And while, ideally, the sustainable building community should try to make use of products that encompass as many green attributes as possible, material durability and contribution to energy efficiency are arguably the two fundamental characteristics on which material and product selection should be based. Structures that are low in operation and maintenance, whose components are well made and thoughtfully sourced, whose interiors provide a comfortable, healthy workspace, and stimulate and inspire its occupants are likely to stand the test of time. Creating buildings that are efficient and enduring and are designed with these materials in mind are key to meeting our larger sustainability goals of energy independence, operational savings, resource efficiency, regional economic resiliency, as well as healthier, happier occupants and reconnection with nature.